All right, recording and speed rolling. We're in the last few minutes of class. I want to go over those solutions with you guys. Remember, the question is, what's the relationship between, say, like M1 and M2 and the acceleration system? Right? And there's two parts: the classic double elevator Atwood and the modified looking Atwood. Right? So I have posters with the solutions on them, but there's actually two different sort of approaches to get to the answer, and the answer is actually underneath these cards right here. Oh, whoops, sorry, that's the modified. Let's start with the classic double elevator. There we go. Again, I've got the answers underneath these cards because I want to walk you guys through two different approaches, maybe like a front door and a back door type approach. Right? So one approach is maybe sometimes I call it like a micro approach, like start from micro and work to the systems. Right? Is to start with these two equations here, based on this here free body diagram. Here's free body diagram with actually it's a couple free body diagrams, right? One for mass 1 and one for mass 2. You guys see that? Right? Do you guys think each of these masses has a weight and also a tension force? Right? And do you guys see how the tension force is sort of like the Goldilocks sized force? Like this tension is larger than the weight of M1, but the tension is smaller than the weight of M2, so that there is a net force driving M1 upward and there's a net force driving M2 downward. You guys see that? Right? Now, I didn't quite ask you guys what is the tension force. We didn't quite go that deep in the slab, but you guys look for acceleration. But I guess you could find that too, right? Right. So what I'll do is I set up a system of equations. One for block 1. You guys see the tension up minus the weight down is going to be mass times acceleration. Hey, there's Newton's second law of motion as it applies only to block 1. You guys see that? Right? I can do the same thing for block 2. The weight down minus the tension force up is going to be the net force, which drives mass times acceleration for block 2. There's Newton's second law of motion for block 2. Right? So now I got a system of equations, 2 equations and 2 unknowns, because you probably know what is M1 and what is M2 and what is G. Like those would be known values. So do you guys see what the 2 unknown values would be? The acceleration, A, and also the tension force, right? So you could solve for both of those simultaneously. Could you guys maybe do some algebra, do a substitution, and solve for both of those variables, the acceleration and the tension force, right? And so you could come up with an expression for acceleration in terms of the masses that way. That's one approach, right? Now, I usually approach this from a macro point of view. So let me slide these cards around a bit, right? And or maybe just here, I'll do this way, right? The actual answer to this lab is actually the second box, which I've been covering up so far. Right? Here's from a systems point of view, right? So here's Newton's second law of motion. But what if I take this to be like an entire system? And from the systems point of view, are these two guys playing tug of war? You guys see tug of war, right? This guy says, "Let's go counterclockwise." This guy says, "No, let's go clockwise." Right? You guys see tug of war? In fact, if they were the same mass, the same weight, it'd be like, it'd be a draw, right? Okay, so that'd be a one boundary condition. So I'm going to take the difference in weights, right? Could you take the difference in weights? M2G minus M1G could be like the net force driving like clockwise versus counterclockwise, right? Right. So for this net force, here we go. Here's the answer reveal. Acceleration is, here's the net force, right? Divided by M total. Hey, how much total inertia is being moved around? M1 plus M2? Because remember, mass is like a scalar value. So you just add those together. Do you guys see that? The difference in weights divided by the sum of the masses. That right there is the answer. Now, if you factor out the G, could be the difference in masses divided by sum of masses all times the gravity field. That looks more like in line with, I said there was some way to multiply and divide those starred columns. The difference in masses, the sum of masses, and G. You guys see how that is? Just factor out the G. Get that, right? Right. Now, you can still get this from this system of equations. I'll go back to the system of equations because I'll normally like if we see this in a textbook question, I'll probably do it this way, macro, and then the follow-up question might be, hey, I wonder what was the tension in the string. But once you solve for acceleration, can you just take that acceleration and pop it right in there and solve for tension that way, or you can plug it in this one and solve that? It may be the same tension, right? Right? You guys think? Right. Are we good? I meant to emphasize that point, guys. One string, I think one string can have one tension, so this would be the same tension force, right? Especially if it's massless frictionless pulley. All right, let's switch over. Look at the modified version, the Hot Wheels car. I'll do the same thing. There's a micro and macro approach. Here's the free body diagrams. So the hanging weight has the weight down and the tension force up. I bet there's more force down than up, right? So it can overall accelerate down. The one on the Hot Wheels car. Okay, well, it also has a weight, but that's canceled out by the normal force, so those are a wash, right? The tension force is what's dragging that individual block along, right? And maybe there's a friction force, but you guys Hot Wheels car, friction goes to 0. So, which is even simpler than what I have on this poster, because friction force was 0 for you guys. Okay? So here's the system of equations. Right, net force on block 1 results in mass times acceleration for block 1. All right, so this the difference between these two, right, is mass times acceleration. For block 2, now for you guys, it was only the tension force was dragging block 2, right? Only the tension force. Now, if you included friction, I guess you'd have to subtract friction. You can do that way, right? So system equations, 2 equations, 2 unknowns. What is acceleration? What is the tension? If you consider friction, I bet you could calculate friction, just be coefficient of friction times the normal force, more like yesterday type stuff, right? That's right, right? Okay. But micro point of view, you could solve for acceleration that way, 2 equations, 2 unknowns. It's system equations. Or if you do a macro approach, you look at this entire system. Guys, what is the only force, if you neglect friction, what's the only force that's acting as the driving force for this whole system? Yeah, the weight of block 1, and only the weight of block 1, because these two cancel out. Tension is just internal to the system. It's just holding it all together. So I've got the weight of block 1 is driving the system. Now, if you did consider friction, you could subtract that. But for you guys, you could just neglect that, right? And what's the total inertia being moved around? Well, that's M1 plus M2. That's the sum of the masses. So that right there, I'm covering up with my thumb the part that doesn't really apply to you guys, right? That's the answer to the second part of your lab. The acceleration of the system is the weight of the hanging one divided by the mass, the sum of the masses, right? You guys said too, right? Yeah. All right. So once you got some data for each one, you guys got the answers. There's the answers for the modified version. There's the answer for the classic double elevator. Go ahead and pop that in the grade tray, and I will give you guys points in the grade book. All right. Oh yeah, just in time. That was our wrap on today.